Hi everyone, welcome to my presentation. This is the building technology presentation. So I have these pictures of the basically Marvel comic superheroes. Um, when we watch these, this one is a one of Superman. So Superman goes through office buildings and you see the kind of destruction that his flights go through. And I guess it's not enough to knock these office buildings down. In this one, you have the Incredible Hulk. You've probably always seen him getting thrown into an office building, but that doesn't actually he makes a severe indentation into the building, but that doesn't bring down the building either. So what I've seen is, and this last one is with Godzilla. Now you could see here that it makes a serious chunk, it takes a serious chunk out of the building, but the building actually still is standing. So the question is basically, how do these office buildings with these supernatural forces, how do they actually remain standing? In a more real life situation, we got 9/11, the Twin Towers. Now the force of the planes getting crashing into the buildings, that actually did not, and the explosives that were apparently in the airplanes, that combined with the force of the airplanes that did not bring down the towers. It was actually later that the fire resulting from the impact that eventually brought down the twin towers. But the initial planes going into the building and the explosives did not bring the tower. So that brings us back to our question: how do these buildings remain standing? So my name is Cyrano Adlawan. I work in commercial real estate, helping companies with their office leases and buildings. I wanted to get a better understanding of the building technology, and my presentation will be on the high-rise multifamily podium structures that we're seeing in downtown LA. Pretty much all the office crane towers that you see are building podium high-rise residential. I want to basically focus in on the lateral stability of these high-rise buildings. Basically, in a real-life instance, seismic events, wind shear factors. How do these structures resist all that? Okay, the building that I will focus in on is the Circa project, which is in downtown LA across from Staples Center. It was just opened about 6 months ago. It's a fully functional, I think the fully functional development. Tenants are already moving into and occupy the towers. It's about 35 stories tall. You got about 8 floors of podium here, and you got a huge LED display, and you've got retail on the ground floor that's just being leased out. There's another picture of it. So before we go into going into the specific Circa project, I just want to outline the but the framework of how lateral stability issues get addressed. There are three methods to provide lateral stability. First is a rigid frame, shear wall second, and the brace frame third. The rigid frame, this is the basic rigid frame. Basically, this is the rigid frame is but it's the least efficient way to achieve lateral stability. It's only good for low to medium rise structures, such as this one. This looks like it's a 4 to 5 story building. As the building increases in height, it's necessary to supplement this with bracing mechanisms, either diagonal bracing or a rigid core. This is an example of a brace frame. You see the brace basically right here. In comparison to an unbraced frame, where if there's a seismic activity, you could see the movement here, as opposed to a brace frame, which is very small. Here is a good example of the braced frame going up the building. In our illustration book, it talks about definitions. An efficient type of high-rise structure is a tube structure that has perimeter lateral force-resisting mechanisms internally braced by rigid floor diaphragms. The structure acts essentially as a cantilevered box beam in resisting lateral forces. So what does this mean? So we're going to unpack these definitions in our construction books. So a diaphragm basically is a flat structure. So it's basically the diaphragm are the floors. The floors are the floor structure in these buildings. The shear walls, the second item that provides lateral stability, acts as a vertical diaphragm. So it says here, the ability of a shear wall to resist lateral loads requires a well-constructed roof diaphragm. So you have these floor diaphragms capped off by the roof diaphragm, and the shear walls, and in this case, the circuit diagram is going to be a core shear. They act basically as a box structure, and then we get to the box structure here. It says when diaphragms and shear walls are used in the lateral design of a building, the structure is termed a box system. Okay. And what is a cantilever? So a cantilever is basically a rigid structural element. An example that I came across was a diving springboard, where it's a horizontal cantilever. So you have the diving board this way, and someone walks up here, the board will flex here, but is rigid here. And basically what the high-rise building, the vertical cantilever is this way. So it might sway up here nominally, but it will be rigid at the very bottom. So that's what a cantilever is. So a high-rise office building is a vertical cantilever. And that brings us back to the Circa project. The side issue that I wanted to make note of is I was always the impression that these podium structures were all above grade. In the instance of Circa, which is 8 grades above parking and then 35 floors at the top for the multifamily residential, it's actually got 2 levels of below grade parking. Okay. It uses the mat foundation structure. See here. And you can notice here that the beginnings from the mat structure, you're actually starting to see the shear wall, the actual coordinates of the steel reinforced shear wall that's going to be part of the core. So you see it one instance here, and there's going to be a second core wall that's going to be developed for the other building, and it's going to run through the below grade parking, the above grade parking, and all the way through the top of the roof of the structures. 4 mat foundations were poured. I didn't see any reference to base isolation mechanisms in my research of these Circa structures, so that was apparently not used. These isolations kind of a give at the bottom, so it minimizes the vibration. Here you go. They're the two, I think the core wall here and the core walls here. Two-way post-tension slab systems. That terminology was explained in our textbook. Note how a portion, so the residential structures are actually being built here, but you'll notice this little indentation where the above residential actually goes into the parking. It's like a nook there, kind of. It's pretty cool design. The shear walls coming up here. So it's actually one structure. The continuousness of the shear wall from the mat foundations is actually one structure. It's actually the parking, it looks like the parking and the buildings are separated, but because of the shear walls from the bottom to the top, it's actually one continuous structure based on the shear walls from the core. Let's see here. First lateral stabilizer is the continuation of this core shear wall from the bottom to the top. That's the first lateral stabilizer. Shear walls definition. Here's an example of a shear wall. You got the core shear wall. You can have shear walls from the outside of the building as well, or somewhere halfway in the building. So you can see here the elevator banks of the shear wall here. The second lateral stabilizer is a rigid frame system. That's basically the exterior of the exterior building. Exterior of the building. You can see here, this is the basic rigid frames. This is the frames here. This would be kind of like the Circa example. Here are the basic blocks we were talking about. In the Circa, you had special moment frames. And basically, this is what the structural engineer of the project, they designed this. So it's weak beam, strong column methodology. What does that mean? So there are two types of steel beam connections based on the American Institute of Steel Constructors. One is the moment connection, which is basically a welded beam, and the other one is called a shear connection, type 2, which is just bolted on. Okay. So here we have the example of a shear frame, which is bolted on. The moment frame gets bolted and welded into the structure. So this is the rigid frames that we're talking about. And for the Circa project, they made use of this moment frames. Above that is the structural engineer used a strong column and weak beam concept. So what this does is the weak beam, if there is, it will collapse. If there is a collapse, they will collapse here. So it'll actually droop down. This will not affect the actual columns. It's strong column. As opposed to a weak column, strong beam, where if it goes, it's less stable. The columns will kick out. So, in the bigger scheme of things, maybe it doesn't, maybe in the bigger scheme of things, it's probably this one is the one you would want to go with. I'm not sure if this one will be, in the real life situation, how much less it will be. I mean, I think this is pretty strong system as well. But Okay, the circuit project getting completed. So in conclusion, 2 levels of below grade parking with a mat foundation, the sheer core walls coming from the foundation through the 2 levels of below grade parking, the above grade parking, and the 35-story residential. All of that with the moment frames and the special weak floor, strong column structure that actually creates a bolt down effect. You see here, the roof diaphragm bolts down the whole entire structure. Well, it actually gives it more stability. So the circuit project is actually an example of the dual system, where you have the central shear core wall and the perimeter frame, the moment frames. Dual system, suitable for 40 to 60 story buildings. It's in other professional, I guess the language is called a tube and tube structure, core and the perimeter frames, floor diaphragms. Okay, the combined situation. I just want to make a note that the importance of the structural engineer in this endeavor. So structural engineer is a little different than a civil engineer. A structural engineer, both are civil engineers, but the structural engineer is a little bit more advanced. They focus in on these issues, and they need more than the typical 4-year degree. In this project, it was CPC, Corey Koposki Company, structural engineers. They're based out of Seattle, and they actually won an award for this. The ACI, American Construction Institute's Charles Pankow Award. So congratulations to them. And that is it. One final note I'd like to mention. When I started out in the real estate industry, I worked with a developer who built most of the high-rise office buildings in Bunker Hill. And when I was meeting there, another colleague of mine who was an oil company executive was talking about how these office buildings in downtown LA, basically if one beam, one floor gives, the whole thing will come crashing down. So I mentioned that to the developer one day, and he mentioned to me that these buildings were basically state-of-the-art, and it's going to take a lot to bring them down. So for years and years and years, I had that question in my mind as to which version is actually correct. So, with this research, I've actually come to the conclusion that the developer is right, and it takes a whole lot to bring these structures down. It's getting back to the DC comics. It's got to take basically a Godzilla effect to bring these structures down. So they're very strong. Okay, thank you very much.